damping mechanism. Okay, that's through the damper. Okay, and now we will see how the energy, there is the kinetic energy and potential energy are taking part in a vibratory system, and we will take a simple example of the or simple pendulum. It's okay, and I think I have this and these two slides I have uploaded in the team also. So this is very simple, and that you might already be aware. So let's say this is a simple pendulum, okay, which is hanging from point O, and L is the length of the pendulum, and the mass length is the bob is the m. Okay, so this is the datum position, that is the undefined position is the position 2. So if I give a little small disturbance, let's say, and move it to position 1 and then leave it, and we know that it will continue to oscillate, and after a certain time it will come down to its rest position. Okay, so what is happening as far as the energy is considered? So you can think about these three positions 1, 2 and 3. Okay, so at position E, as you know, also here the velocity is the 0. Okay, so therefore the kinetic energy is the 0, because kinetic energy half m into velocity square. Okay, so here the potential energy is the maximum, because it's the maximum path travel basically as far as the point 2 is concerned. So with respect to point 2, it has moved the farthest to a point 1, so it is the maximum potential energy. So the total energy is basically potential energy at position 1. Okay, right? Here the velocity is maximum. So now you see, so when the bob is at position 1, so the weight is acting in the downward direction mg. So due to this weight, there is a clockwise moment, right? Clockwise moment. So as you see, clockwise direction, there is a moment, it is acting, it's torque basically, it induces, which is the value is mg multiplied by the distance traveled. So what is the distance traveled? So you can, from the trigonometry, you can very easily find out. So if this what's called, yeah, just a minute, right? This color is okay, yeah, anyway, no problem. So the distance, this height is L into 1 minus cos theta, and this horizontal distance is basically nothing but the L sin theta. Okay, so this is L sin theta, so mg L sin theta, it is providing a torque. So and due to that, it will be angular acceleration, it will create. Okay, and it will come from position 1 towards the position 2. So when it comes to position 2, you see the all the potential energy are converted to the kinetic energy. So here the velocity is become velocity is become maximum. So here, like, the velocity is 0 at the position 1, so the kinetic energy is 0, and the position 2 velocity is maximum, so the kinetic energy is the maximum. Okay, so it will since there is a kinetic energy, so it will continue to move, it will not stop at the position 2, and it will continue to move. However, as you see, as you move from the position 2 towards the position 3, so there now the weight is acting like this, and there will be counterclockwise torque, right? So it will be, there will be deceleration as it moves towards like this. So there is a deceleration, at some point, at point 3 will come, the velocity will be 0, and again the potential energy maximum. So this thing continue to be happen, and the bob will oscillating. Okay, but as you have seen for a actual system, so it will not for the infinite time it will not oscillate. After certain time it will come to the rest due to the resistance, or as we call it, the damping in our dynamics term, provided by this. Here in this case, it is the surrounding medium. So there is some energy distributed in each cycle of vibration, right? Okay, so that is called the damping. So now there is an important point, that is called the degrees of freedom. Okay, so before coming to that, so I will just ask you here. So can you tell me, for this thing, what is the, I mean, how many degrees of freedom, or the, if you do not understand the degrees of freedom, I will define that. So let us tell me how many coordinate system is required to describe the motion of this mass completely. Okay, how many coordinate systems are required?
2, sir.
2.
Huh? How many?
2.
What are
sir.
the two?
R and theta.
What is R?
Sir, R is the radius of the circular, and then theta is the angular displacement.
R means you are talking about L, right?
L, sir. Yes, sir.
So L is fixed. L is the length of the L is not changing, right? Correct?
Sir, X and Y.
Someone has said X and Y. Someone is saying theta, only theta, right? Because L is fixed, right? Anything else?
Yes, sir.
So this is 2, this is 1. Then, or all 3 is required? I don't know. All 3. or a combination, whatever. So anybody else, what is the, so this is basically how many coordinate system required to describe the motion of this mass completely is called the degrees of freedom as far as the definition is concerned. Okay. Okay. So in this case, the number of degrees of freedom, degree of freedom as is written in an abbreviated form DOF is 1. That is basically the theta. So then you can question, or I can raise the question, why not x, for to define this position here. So I need how much x from the position x and how much y is there. So this x is, but you see x and y are not independent, right? So they are dependent through this relation L. How it is? X square plus y square is equal to L square. So the definition read like this is for the degrees of freedom, number of independent. So that is a very important thing, and here this line is the important thing. Okay, number of independent coordinates required to describe the motion of the system completely. Okay, so for this pendulum system, so it is a theta is the only degrees of freedom, which is abbreviated form. We can usually call it single degree of freedom system. So this name is called single degree of freedom system. Clear? So just keep in mind these two terminology. It has to be independent coordinates, and it will completely describe the motion of the system. Okay, so in this case, theta is the only coordinate. Okay, or in other words, you can say I will use x, and then there will be constraint provided on the other degrees of freedom. So basically, this is the best way to describe the motion, right? Okay, so as I told, the Cartesian coordinate x is required, but they are not independent. So because they are related through this relationship. Okay. So thus any one coordinate can describe the motion of the pendulum. So here the theta is the more convenient, as I told. So sometimes this is called the generalized coordinate. Okay, so instead of the xy is the Cartesian coordinate, so instead of this in dynamics you refer the term generalized coordinate. Okay. So now based on this number of degrees of freedom, the dynamic system classified as a single degree of freedom system and multiple degree of freedom system. Okay, so obviously as the name suggested, the single degree of freedom system has only one degree of freedom, and the multiple degree is more than one. So even 2 degrees of freedom system is also called a multiple degrees of freedom system. Let us see some of the simple example. Okay. Okay, so we'll discuss about the thing. So this is, you see, this is called the discrete mass, right? This is the discrete mass. That is basically the rigid mass. Okay, right. So this is one coordinate is good enough to represent the system motion. So this is a single degree of freedom system, a spring mass system. Okay, so like its equivalent torsional system, if I consider, so 1 theta. Let's say this is the disk. Okay, this is rotating. Okay, so then theta is the only degrees of freedom. In this case, the two masses are connected by the K1, K2 here. So for this case, x1 and x2, so it's a 2 degrees of freedom system, right? Similarly, the torsional system, the 2 disk is there, so theta 1, theta 2, so this is the 2 degrees of freedom system. In this case, you see it is a combination. One is the translation degrees of freedom x of this mass, because this mass is constrained to move only inside this portion, so it is the x, and then the bob and this pendulum type of system, that is the theta. Okay, so in this case, the x and theta is the 2 degrees of freedom system. So it can be combination of translation and the rotation also. Okay. Right, so sometimes that's why they are called like q1, q2 call it. Okay, so these are called the generalized degrees of freedom. There are q1 is x and q2 is the theta. Okay, so these are all, you see, the discrete type of system, right? M1, M2, M1 here the discrete. So the masses are actually the lumped, right? 1 plus is the lump. So it is a triple pendulum system. It's a 3 degree of freedom system. So these all fall under the category of multi-degree of freedom system, except these and these. Okay, these are single degree of freedom system, and these all are multi-degree of freedom system. Okay, because degrees of freedom is more than 1. Okay, understood. So here also in a similar manner, you can see. So instead of, it is not a 6 degrees of freedom, x1, y1, not x2, y2, or x3, y3. It is because they are related through this length. So that's why it is the theta 1, theta 2, and theta 3 are the degrees of freedom. That is the 3 degrees of freedom system. So as I told earlier, coordinate necessary to describe the motion of a system constitute a set of generalized coordinate at q1, q2, and may represent Cartesian and or also non-Cartesian coordinate. So it can be Cartesian coordinate, it can be some non-Cartesian coordinate, or a combination. Okay, right. Okay. So as I just use the terminology discrete. Okay, so discrete means here you see the masses are separated and they are lumped at a one point. They are basically rigid mass. Okay. So but in our actual system, I mean most of the actual system, real life system structures are continuous in nature. Okay, that is the parameters are not like lumped at a particular point, like say beam, like a cantilever beam, right? Or bridges. Okay. or you see most of the, I mean, the structural engineering examples, like a tower, this is a distributed, right? This is, I mean, as far as the tower is considered, okay, let's say this is a tower, okay. So in this tower, there are, I mean, the mass is distributed, or the cantilever beam shown here is the mass and all the properties basically, not only the mass and the stiffness properties are distributed, as opposed to the simple configuration that I showed here. So here the spring is here, mass is here only, okay. So that's called the lumped parameter system or discrete system, and this type of systems are called the distributed parameter system or continuous system, because parameters are distributed along the length or whatever, okay. So the major difference is that, as you can see from the slides, so it has a finite number of degrees of freedom, as you can see here. So it has 1, 2, 3 degrees of freedom system. I mean, as many masses is there, and if I consider only translation motion is possible, okay. If there are other degrees of freedom also, but it is a finite, it's not infinite, right? Okay, it is finite. So the parameters are lumped, as I told, okay. And as you will see shortly after some time, maybe or in the next class, so that it is governed by the ordinary differential equation, okay. It's the ordinary differential equation, okay. And for the continuous system or distributed parameter system, as you can see, let's say cantilever view. So how many degrees of freedom to describe the motion of the system completely? You see, it is all, everything is distributed. So I need each and every point, and the number of points is infinite, okay. Here it is, I'm showing x1, x2, x3 some point, but there are here also, in between also many. So actually, ideally speaking, it's infinite number of degrees of freedom, okay. But obviously, in simulation purpose or calculation purpose, we will not study with the infinite number of degrees of freedom, right? Okay. So we'll, in most of the cases, we'll approximate it as a discrete parameter system through some approximation, okay, and then deal with it, okay. So parameters are distributed. That is the most of the real system we handle it, and the important thing is it is described by the partial differential equation. That we will see at the end of the course. We will come to, then we will discuss about the continuous system, okay. So first we will discuss about the single degree of freedom system, then the multiple degrees of freedom system. So those are all based on the basically lumped parameter system, okay. Okay. So you see discrete versus distributed parameter. So most of the time continuous system are approximated as discrete system, as I told, to simplify the analysis, okay. So as you will see later that this, so basically what you have to do, so once we set up the differential equation, that means the equation of motion for the system, okay. So you have to solve it, right? To solve it, to get out the, to find out the responses. That is your main aim basically, okay. So to solving a partial differential equation much more difficult than compared to the ordinary differential equation, and this becomes more complicated, and even in some cases it's impossible to do if the system is become very complicated, or the system is not a kind uniform type. Let's say this simple cantilever beam, right? If it is a prismatic or uniform in nature, homogeneous in nature, then you can solve the partial differential equation and get a closed form solution, okay. But if let's say this is a tapered beam, okay, or if there is a twist in the beam, right? Beam, there is a twist. It is not, I mean, the axis is not straight. There is some twisting in the there, okay, twist in the beam in there, or not a homogeneous material. It's like a different materials is made, okay, made up of different materials. Or what should complication will be there, or some different complicated boundary conditions, okay. So in that case it is very difficult, or in some cases it is impossible to solve a partial differential equation. So in that case you have to do some approximate method to solve it, okay. Right. Okay, so what you do, so you do sometimes suitable lumping, that's called the discretization, and the discretization approach is better done using the, just remember the terminology, you don't have to know that, this is the finite element method. It's called the finite element method. You have not learned it, maybe, I don't know, in the 4th year there will be with the course, maybe there, finite element method. Okay. So through this the discretization can be done, okay. Just remember the terminology, nothing else, okay. Okay, so now we will discuss little bit more detail about those elements that I mean what is called elements in the discrete parameter system, okay, characteristic. So basically the elements we talked about, right, the spring element, mass element, and the damping element. So what are those and how they are representing the forces, okay. So there's the so one is the spring element, right, and another is I called is the mass or inertia element. Inertia element, and other is the damping element, okay. So that I will read later. So spring element, what is do, it's relate the forces with the displacement, okay, and it's stored, as I already told, as the potential element, okay. So the forces, as I already told, so if this is a spring, so this one, this is the forces Fs is acting here, and let's say this displacement is x2 and this is x1, whatever it is k. So then I already told the spring force Fs equals to k into x1 minus x2. Sometimes this force is also called the restoring force. Why it is restoring force? Because this force which is trying to restore the spring is the initial configuration. Okay, so this is the spring force. Remember it. Okay. So this is basically, that means what I am saying, that the spring force which is proportional to the relative displacement. Okay. So if I draw this figure, Fs, I think it is in the slide. Just let me check after some time. Okay. So the spring force which is proportional to this relative displacement. But if the spring is non-linear, it can be, or the deformation becomes large, so it can be after some time becomes like this, can be like this. So if the behavior is like this is called the what I think stiff spring. It's called the stiff spring, and this is called the soft spring. But obviously we will not deal with type of this, or all the systems will be linear. Okay. Let us see. Fine. So this is the spring element. Okay. Yeah, so elements constituting a discrete system are three types. Okay, so spring elements, so component relating to the displacement. As I again the same thing. It is this is the linear range basically. So here, so obviously you have to keep in mind that all our study will be based on the small deformation, right? Small deformation theory, small motion about the equilibrium position. Okay, not the large deformation, because in the case of the large deformation, the system can behave in a non-linear manner. Okay. Okay, so this I have already told. So this is the elastic restraining force, as this force tends to bring the springs to the unstressed configuration. Okay, yeah. So now tell me, what is the unit of this K? This is called the spring constant, right? Or stiffness. So what is the unit of this K? Yes, quick. In SI unit, you
Newton
can
per
tell.
meter.
Newton. Very easy. This is in the force unit. This is in the displacement unit. So you just divide it. Okay. Now then comes the, first discuss the inertia. The damping is a little bit different, so we'll discuss about the damping just after discussing the mass of inertia. Okay, so this is very also simple, the mass or inertia element. Okay, so this relates the forces with the, so I am just showing is the Fi or Fm also you can call inertia force, Fi or Fm, whatever. So Fi is related with the acceleration. Okay, it relates the forces with the acceleration. So in this case, the discrete mass I am considering as a rigid body. So if it is moving in acceleration x, okay, and then the force is Fm. So as per Newton's law, so the force in that direction equal to mass into acceleration. Okay? So that is called the inertia forces. Okay. So here also I can plot like this. It's double dot if I am using, so if I like this, right? That's all. Okay, so this, so we have to deal with the basically two things. One is the m, that is the mass. Okay, and another is the k, right? Okay, now the third is the damping element. Okay, damping element. So as I told, it is basically the representing the energy dissipation mechanism, right? Energy dissipation mechanism. Patient. Somehow the energy is getting dissipated, otherwise how come it is going to the rest position or its initial configuration, how it is coming. So somehow the energy is getting dissipated, right? Because through some initial displacement I am providing to get the vibration, or if there is some force excitation, okay, outside force is applied. So it is just imparting some energy. Okay? So in order to come to the rest, there should be some energy dissipation mechanism there, and that is through the damping element. And the converted I mean, the dissipated energy can be converted to the heat or like sound, so those type of things it is converted to. Okay, so it is actually very difficult to determine the damping in the actual practical system. Okay, so what are the most easiest ways to model the damping is called the known as the viscous damping, and which we will going to consider in most of those study. Okay, the viscous damping, which is also called the velocity proportional damping. Okay. proportional damping. You see the two things that you have done. One is the spring, which is relating the forces with the displacement, right? And another is the mass on inertia element, which is relating the forces with the what is called acceleration, correct? Okay, now this will relate the forces. So what you show FD damping, FD. So this will relate the forces with the velocity, okay? The relative velocity. I'm just writing an extra here, okay? So the what is viscous damping? So viscous, as you see, the terminology meant is that the viscosity, right? Viscosity of the fluids or the air or whatever it is, okay? I mean the liquid or the air, okay? Like oil. So it is represented like a cylinder type cylinder, and then there is a piston is there inside it, and there is a, let's say, oil or water filled with this. Okay, so this oil or water has some viscosity. So this when this piston moves, so this oil or the water, whatever it is, so it provides some resistance to this motion, and thereby dissipating the energy. So this is the basic mechanism that we consider for the viscous damping model, and it's usually shows to this. So you will come to this type of configuration in the books you'll find. Okay, so this and so these are forces. It's FD, right? FD. Okay, so I'm calling this FD is basically proportional to the change in the velocity. Okay, so if this is x2 dot, this is x1 dot. Okay, so then I can write x2 dot minus x1 dot, and if the proportionality constant I am taking as a c, so x2 dot minus x1 dot, the c is called the coefficient of viscous damping. This is called coefficient of or viscous damping coefficient. Viscous damping. Right? So again I can plot here like this. So this is x2 dot minus x1 dot. This is FD. Okay. So this is representing the damping force which is related to the velocity. Okay. Okay. And the damping force is what is called, it is resist the increase in the relative velocity. Okay, that's why the term also the damping is somehow related to this thing. Okay. Now tell me what is the unit of C? Yeah, come on. What is the unit of C?
Newton second.
Newton?
Newton second per meter.
Newton
Per
second.
meter.
Okay. Good. Be careful about that. This is the unit of the damping. So this is the most common type of damping that you used. There are some other damping that not used extensively, but just remember that one is the frictional type damping due to the frictional resistance. Like I think you might be aware that this is the Coulomb damping. It's called the Coulomb damping actually, or the dry friction damping. Okay, so that is due to the friction. But in that case, what is happening here? You see the damping force FD, right, is C multiplied by the relative velocity. So as the relative velocity is getting changed, so the damping force is also changing, right? But in the case of the Coulomb damping or the dry friction damping, the damping force is constant in magnitude, okay, and it is opposing the motion of the vibrating body, okay, and is mainly, as the name suggested, the dry friction. So it is caused by the friction between the surfaces, okay. Okay. So let me go to the slide, then it will be easier for you. Okay, so this we have already discussed, right? Spring element we have already discussed. Okay, so this I missed actually maybe, but this is already, I mean, this is very well known to you, right? Strings in parallel. Okay, so there can be two springs there in parallel, two springs, say string or multiple spring can be there, which can be in parallel or which can be in series. Okay, so then you can find out the equivalent spring constant, right? So if the springs are parallel, then you see the forces are different in the two springs, that is Fs1 and Fs2. So then I can find out the total spring forces, that is Fs1 plus Fs2. So I can write this as an equivalent spring. I mean, this means I want to replace this thing by using an equivalent spring, right? So this is K equivalent. Okay? So that K equivalent can be written like this. That is, I think, you all know. And similarly here also, in this case, the forces are same in the two spring when it is a series. Okay, so then I can find out the equivalent spring like this, constant like this. Okay, equivalent is this. Okay. Okay, no, I missed anything. Okay, now, yeah, so I'll come to this thing later. So what I have discussed, let me tell you anything is, yeah, damping I've already discussed, right? So damping element is relating the force to the velocities. So it's represent the frictional characteristic and energy dissipation of the structures. and the vibrating energy is gradually converted to heat and sound. Okay, so this mechanism actually basically is called the damping. Okay, so this also I have, I think, discussed. Yeah, and this is called the dashboard also sometimes. Okay, this system, this configuration, that's we sometimes call the dashboard. So in sometime in books you find out, maybe found out that the this system actually. So right now I can write like this. I can show this figure. So I showed this, right? Correct, with mk. So now if I add the damping, okay, something like this. Okay, so this is basically a single, it's called single degree of freedom system, right? The only one x coordinate is required. It may be subject to some forces Ft. So this is called single degree of freedom system, and that is called spring mass dashboard system. Dashboard system. So this is actually called the dashboard. Okay. So these are the most commonly used in the vibration analysis. Okay. This is also I told, and you told that the Newton second meter is the unit. Okay. Okay. Then the Coulomb was the dry friction damping. Okay, so that is due to the friction characteristic. So just remember that this is the constant in magnitude, but opposite in the direction of the motion of the vibrating body. Okay. Then there are another kind of thing is there, which is called also the history damping or the material damping. Okay. Also and also called the structural damping also sometimes. Okay. So it is the I mean when the material is got basically deformed under the load, right? So if we plot the load deformation curve out here, it is the basically the stress strain curve shown. Yeah, it is bracket, it is written force displacement. So if I plot this diagram, force displacement diagram, so you'll see the load path and the unloading path. I mean the loading path and the unloading path are not same. Okay. So if I see under this diagram, right? So under this loading diagram and unloading diagram, if I plot, so this ABD basically, right? So this ABD basically means that the whole part basically it is showing. This whole part, right? This ABD is showing this part. This part is the energy provided basically, right? Energy that is expanded. Okay. Then this much is the recovered energy, the lower part that is remaining, because the unloading path is like this. Okay. So that means this much is the dissipated, this portion. Okay. So this is called the history damping. Okay. Okay, so we'll see how the structural damping can be related to the equivalent viscous damping. Okay, because you see this thing is easy to handle, right? Because here we know that the damping force Fd, where is that? Yeah, the NP is this like this. So if I can use this type of simple thing in our equation of motion, so it is much easier to handle. Okay. So therefore, we'll try to find out the equivalent value of this C, that which is the coefficient of viscous damping in terms of the structural damping. Okay, so how to do that? That is through usually experiments. Okay, so that I'll try to demonstrate, I mean show in the maybe some few classes later. Okay, this also we have discussed. Okay, right. Okay, now you see, so I am only discussing about the translational degrees of freedom, right? Translational degrees of freedom. I mean, I have shown, what is that gone? Yes, so I am talking about this k into x2 minus x1. Okay, so it can be also for the torsional system also, right? So torsional system, the F spring force, right? I mean the Ft I phi, right? So Ft torsional system, so it will be k theta, that is the torsional stiffness, minus theta to minus theta, like this. So the equivalent system exists. So that is what I am saying. So the torsion system, it will be like this. So that is given here. You can see. So mass will be now replaced by the mass moment of inertia. Like basically the M will be replaced by I. Spring K, what I am saying, it will be like K theta or KT, and C will be like the C theta or something like that. Okay. So that's the analogy basically between those translation system and the rotational system. Okay. Now when you're talking about the stiffness, right? So how to find out the equivalent stiffness for those types of system? Okay, how to find the equivalent spring constant, right? So this is, let's say, x bar, which is undergoing only the axial motion F, right? I mean, subject to the force F and doing the axial motion. So let's say due to the load F, the axial force F, the delta is the stretching. Okay. So then how to find out the spring constant? Okay. So as I have you already seen, the spring constant, which is nothing but the force required to produce the inner deformation, right? That you already know. You see from this definition also you can see that, so the spring constant K is nothing but if this is equals to 1, right? If this is equals to 1, then K is the Fs. So that means the force required to produce unit deformation. That's the spring constant, correct? Okay. So with keeping this thing in mind, so what you can find out, so we know that, let's say under the load we know the deformation, and this is the original length, undeformed length. So you can find out the strain. So this is the strain. Strain is change in length by original length. So delta by L, correct? Then stress. linear system, okay, linear elastic system, obeying the Hooke's law. So sigma equals to E into epsilon, right? E is the modulus of elasticity. So then what is stress? F by A, force divided by the cross sectional area. E multiplied by the epsilon I am substituting here. Okay, so I can write F by delta, which is nothing but the spring constant, right? Because force is required to produce the any deformation. So F by delta, I will get EA by L. So this is EA by L. So remember this term EA by L as the spring constant for axial deformation of a ball, right? So I can represent this as an equivalent as this thing where K is this. Got it? Okay. Similarly, for cantilever beam under this thing, okay, under subject to point load, which is W at the free end, at the deep end, okay. So that you already know, right? Delta equal to WL cube by 3L. So that is the vertical displacement at this end. So I can call it a K W by delta because W is the load, delta is the this thing, deep end displacement. So I can find out 3 by L cube. Okay. So if I want to represent this as this thing, as a single degree of freedom equivalent spring mass system, so I can call it this is my spring, this is the weight is hanging, and this is the equivalent spring stiffness. Okay. Now, what is this? The thing similarly for the, if I can try to understand this for the pendulum system. Okay, so for the pendulum system, so as I told, the spring force is the restoring force also, right? Because it tries to restore the system in the original position. Okay, I already mentioned, and it is also written here. Elastic restoring force, Fs, as the force tends to bring the spring to the unstretched configuration. Okay. So similarly for the pendulum also, so there is a restoring force. So instead of here force, it is the torque basically, as I already mentioned. So it is mg into L sin theta, right? This is the restoring moment here. Okay, correct. And if we assume that the theta is small, so then the theta sin theta is theta. Okay, so I can write this is mg L theta. Okay, so this is basically the torsion force, that is kt. T is equals to kt, right? Kt into theta if I write. Okay, so this is basically the restoring force, which is T, and now T I can represent it like a kt into theta, right? Like I am representing Fs equals to k into some x, right? Relative, whatever x is. So here theta is the relative. Okay, here theta is 0, so here the theta, so theta minus 0 basically. So kt into theta. So instead of k now it is a rotational system, so it is a kt I am calling it. So you can easily compare and see that the kt is the mg. So I can consider in this case as the rotational spring stiffness as the this thing. Okay, mgl. Okay, this we have already discussed. Okay. Okay, so now tell me any doubt so far. Okay, then we'll move to our next thing, and then this may be, I think, the equation motion or what it is. So if any doubt, you can ask me. I think this is very simple thing, straightforward thing. But I will suggest to you to read books also. The actually the PPTs are also good enough for initial understandings, and at the elementary level it's okay. But to more understand more detail or get a feel of the subject, or if you're more interested, then you should refer to the books. Okay, I have already mentioned some books, right? And I hope you will be able to get the soft copies of that. Okay. So can you write? So I want to know. Please write in the chat box. So which books now are you able to download it, and are you referring? Can you write in the chat box, please? Or no book yet? Clap and punch. Okay, someone has written clap. Okay, very good. Then SS Rao. Okay. Okay, and the PPT that I am sharing with you, you might find that don't get confused by that. It is a combination of many books. Okay, so some people initially might thought that it is teaching from the SS Rao, right? But it is not like that. Okay, some part is from maybe from the SS Rao. Many other, even some other books are also there. But although it is in the elementary level, so I'll not go into much deeper or rather difficult things. Okay. SS Rao, clap and pen. Anybody else? Only 2 people has replied. Yes. Nobody else? Please reply in the chat box. What books we are following? At least let me get an idea. Or there are some other books also you can follow, and then no issue with that. But these are the standard books which are the you'll find much easier to understand. Yes, anybody else? Nobody, okay. So I hope so till now there is no doubt. Okay. So now let us go to the next thing, which is also basically a part of the introductory thing. We have not actually entered the derivation of the equation of motion and how to solve that. So that will be the starting point. Okay. So that we have not reached there so far. Okay. So the presentation, I hope it is visible, right? Yes. Yeah. Okay. So it is calling that vibration analysis procedure. So I have to analyze it, right? So a system undergoing vibration, whether it is oscillatory motion, structural dynamics like buildings, bridges, aeroplane, or whatever, wind turbine. Okay. So undergoing vibration. So we need to analyze that. So these are the basically, I mean, in general, some steps that we usually follow. Okay. So first of all, you know that our actual system, the practical system, are very complicated, right? There are a lot of things is there. So you need to sometime, in most of the time, you have to idealize it for the to develop the mathematical model. Okay. So some idealization should be there. Okay. Like the way I'm showing, right? So this is a spring, this is a mass. Okay. So there is some systems idealization. Okay. So that our development of the mathematical model, which will lead to the differential equation, that is the next step. Okay. So governing differential equation, which will be ordinary differential equation for discrete system and partial differential equation for the continuous system or distributed parameter system. Okay, we mentioned, right? Okay, but just right now concentrate only on the discrete parameter system, because we will discuss about the continuous system or distributed parameter system in the almost at the end of this subject. Okay, when we will treat the continuous system. Okay, so right now let us consider that the only the discrete system we are talking about, and it is governed by the ordinary differential equation. Okay, so we'll come to that, how to first develop the differential equation. So once the differential equation is developed, you need to solve it. Okay, because in static problem that is also what we are doing, right? That k stiffness, that k into basically x displacement is equal to force. Right? So we are finding this, you know, the stiffness and the force. So we are finding this x. So here, as I told, some additional terms will be there. Okay, when we do the this is the static equilibrium. Now it will be the dynamic equilibrium, and it's called the equation of motion. So the solution of the governing equation, and then from that, as I told, what parameter I will get: displacement, velocity, acceleration, member forces, like those things, and we have to interpret the result. So these are the basic steps. So what is this idealization means? Okay. As I told, so the purpose of the mathematical model is to represent all the important features of the system. Okay, so the idealization should not be such that, I mean, you just miss the important features. So then your mathematical model will be totally different from the actual system, right? You should closely resemble or closely represent the important and characteristical feature of the system. Okay, right? So then there is one term is called the model updating. What is the model updating? Just remember the terminology, nothing else. Okay, this terminology. So it is that. So what you will do? So if there is a complicated system given to you, so first of all you don't know how exact model. I mean, not exact. I mean, what will be the best model it is. So you just first do a simple, very simplistic model, which may be totally crude or totally maybe giving very different result as compared to the experimental results or whatever. So then you can update the things. Okay, no, this this idealization is not correct, so I'll modify it. Okay, so that is called the model updating. Okay, so as I told, actual physical systems are very complicated, so we need idealization and some assumptions, and to do the idealization we need some assumptions. Okay, okay, so you see the idealization and mathematical model. So let's say this is a bike rider. Okay, so how to model is through the spring mass damper system. Okay, so one thing you can do it is a simple model. You see on the left side the figure B, right? So what you are doing, some equivalent masses. So that's basically the mass of this rider and the vehicle, and this is the equivalent springs and equivalent damping. Equivalent spring of the what? This is the tower as well as the tire as well as the strut. Okay, So this is a combined model, but which is a very crude model. You see, this is highly approximate. So you can refine it further. You see, so here it is the mass of the vehicle and mass of the rider is given here, and then the mass of the weight of the wheel. Wheel is taken at the separately, and then in between it's there. It is basically the two tire is given like this, and then there is a two strut, right? This strut is given like this. The KS represented by KS, and then this. So this is basically a kind of a updating, more refining. That can be further refinement also there. Okay. Okay. Similarly, you see, like this is a very tall system, tall structural systems. Okay, I can idealize it as a just a cantilever type of system. Okay, with a mass which is attached at the top end. So I can consider this, idealize this as an equivalent single degree of freedom system. This is a S-DOF system. So I'll frequently use this terminology, single degree of freedom system. If there is more than 1 degree of freedom, this is a multi-degree freedom system. Okay, right. So this is a single degree freedom system. We can treat it. So can you give one of the example where I can treat a structure like this? Practical example. Yes.
So the water
So light poles.
Huh? Yes, tell me.
water tank.
Yeah, water tank, exactly. Water tank, yes. So the example is that water tank. Because there is a lump masses is there, and as compared to the mass of the tank, I mean this the column or whatever is there, so this is we can ignore it. The mass of this tower can be ignored. Okay, as compared to this, I'm talking about. Okay. And then there is, let's say, be a single portal frame type of building frame is there. So this can also be idealized as a single degree of freedom system. Although in reality it is not a single degree of freedom system. There is a column, there is a floor. It can have this motion, then the wind torsional motion also. If it is an unsymmetric type, but you can assume by just providing an assumption that the flow is rigid. Is it very this assumption? If I provide that the flow is rigid, that means it can move only in its plane. Okay, like this, that x and can be defined through the x, and the column masses are much less as compared to the floor mass. Okay, the mass is negligible as I have written here, so you can idealize this as a single degree freedom system. Now tell me, what is k here? What is k here? What is k here? If I represent this system as an equivalent single degree freedom system, so what is k represent here?
So 3/2 EI by LP.
Basically the column stiffness, right?
Yes, sir.
This is the column stiffness I am talking about. So you see the column masses we are not talking about, and mass is the only the floor mass. The second thing is the derivation of the equation of motion, which is one of the most important again coming into the picture. So how to derive the equation of motion? We will see in the next class maybe how to derive the equation of motion. Okay, this thing I have already mentioned. Okay, that for the discrete system is ODE, continuous system. It is PDE. System can be linear or non-linear, because part of the system can be behaved like a non-linear manner also, or the whole system can be behaved like a non-linear manner also. But in our study, we will consider only the linear system. So that the what? So for the linear system, what is the main characteristic of the linear system? Yes.
Hooke's law is valid.
Huh?
Hooke's law is valid, sir.
Oh, there is special, but I mean characteristic. Yeah, you are right. Hooke's law is valid, but that is for the material point of view. If the system is linear, what assumptions is valid? What thing is valid? What principle is valid?
Energy conservation.
Huh? What
Ener-
consideration?
Energy conservation.
Energy is conservative. Energy is okay. No, I am not going to the energy. Energy is fine. No, I am saying, let's say this is a cantilever beam. Okay. This we have already learned, right? In mechanics or strength of material, whatever. Let's say it is subject to distributed load as well as point load here. P W per gram. This is the length L. Now I ask you to find out that what is the displacement here after the deflected surface. Okay. So what you used to do? How to find out delta?
Plus
Yes.
superposition.
Huh?
Virtual work method.
Principle of superposition.
Principal virtual. So in that what you are using basically, and basically if I separate it out, so I can treat this system like this, right? This one system plus the another system with only load P. Can I call it? Is it right?
Yes. Yes, sir.
Yeah.
Yes.
So this thing is valid only for the linear system, not for the non-linear system. Okay, this is called the principle of superposition, right? So this principle of superposition is valid only for the linear system. Okay. Okay, so can be derived conveniently by drawing the free body diagrams of all the masses involved. Okay, so if it is a single degree of freedom system, so you have to write the free body diagram of you have to draw the free body diagram of the single mass. What are the forces acting on it, and then just use the force equilibrium. That's all. Okay, you can do it. Okay, as you will see that this can be more conveniently done using the energy approach also. Okay. I think it is there maybe, yeah. So you see first is the Newton's law of motion, second that is very much well known, so I am just not going into the much discussion here. So when I am going to discuss about the formation of the equation of motion, that time we'll come into that in detail. So you can just go through it, you know it that force, the resultant force in the mass is the mass into acceleration in the particular direction. Okay? That is Ft equal to mass into acceleration. That Ft includes in our present case maybe the elastic forces, damping forces, or any other external forces if at all there. Okay, so that equals to nothing but mass into acceleration. Okay, so now you see this Newton's law can also be written in the form, so I can write this equation Ft minus m into x double dot equals to 0, right? So this is basically a dynamic equilibrium equation, right? So what D'Alembert is saying that, as far as the, which is also popularly known as the D'Alembert principle. Let me see in the next slide. Yeah, so I can write this as this, right? So I am just artificially imparting a dynamic equilibrium. You see, that's like equilibrium, left hand side equal to the 0, right? So through this some fictitious forces, right? This fictitious forces, which is called the inertial force. Okay. So this is a state of dynamic equilibrium, right? This is a state of dynamic equilibrium. Okay. So this is another fictitious. This is a fictitious force which is not present. I mean, which you cannot see there. Okay. So that is called the inertial forces. So this inertial forces is proportional to the acceleration and it opposes the acceleration, right? It is proportional to the acceleration. This inertial forces is proportional to the acceleration of the body. I mean, here in this case it is just a lump mass, and it opposes the acceleration. So that concept which is called the D'Alembert principle. Okay. So the mass developed inertial force proportional to the acceleration and opposing this acceleration is known as the D'Alembert's principle. Okay. So you might not find any difference with this expression and writing this expressions. Okay. But it will be helpful for the multiple degrees of freedom system to write the D'Alembert's principle, and especially for structure or system subject to ground motion. It will be much easier to formulate the equation of motion, and much more convenient using the D'Alembert principle. So just remember that. So this is a fictitious force which is known as the inertial force, okay, which is proportional to the acceleration and it opposes the acceleration. That the principle or the concept is called the D'Alembert's principle. Okay. So using that also, I can formulate the equation of motion based on this dynamic equilibrium approach. Okay. Right. Yeah. So as I told, this Ft, right? So this Ft, what is the Ft? It is all other forces. So that can be elastic forces due to springs, right? Viscous forces due to damping, or any other external forces, that Ft that we are calling it. So it can be, this is K into X, C X dot, relative displacement talking about, right? And this is the external load is this thing Ft or like that. Okay. Yeah. Now then coming if the structural system is more complex, direct equilibrium approach can be difficult. Okay, so I'll just stop in 1 minute. Okay, so although we are not going to use much about the other two approaches, so we'll mostly consider on the Newton's second law of motion to derive the equation of motion, which is convenient for the simple system. But if the simple is highly complicated, it is very difficult to obtain the equation of motion using Newton's law or even with the D'Alembert's principle. So in that case, the principle of virtual work, along with basically the principle of virtual displacement, along with the is called the variation approach, or also known as the energy based approach. It is basically the energy based approach. I'll show some example, then it will be clear to you. Okay, energy based approach will be much more convenient. Okay, which will finally lead to the Lagrange equation of motion. I'll show you what is Lagrange equation of motion and how to derive the equation of motion with that. But I will not derive this thing. How is the Lagrange equation of motion coming? Because that is not actually in our scope of the syllabus, and it is not required at the right now at this moment. Okay, so this variational principle is basically an integral formulation. So the main idea is coming from the Hamilton principle. Okay, it is again the energy conservation approach. Okay, based on the kinetic and potential energy. The advantage of this over the Newton's law or the D'Alembert principle is that you see there we are treating with the displacement and velocity, which are vector quantities, right? And here we are dealing with the kinetic energy and the potential energy, which are scalar quantities. So it can be much easier. Okay, and as you are intuitively understanding that for some complicated system, as let's say just consider a wind turbine blade, or let's say helicopter blade. Okay, so if you want to do the dynamic analysis of that, so writing the equation of motion for those systems using Newton's law will be quite difficult and also time consuming, and sometimes there is a high chance that we will make a mistake on that. So in that regard, the Hamilton principle and finally the Lagrange equation of motion will be much more convenient for that. Okay, and principle of virtual work also will be used in conjunction with the Hamilton principle to make the things more convenient. Okay, so that you know, right? If a system is in equilibrium under the action of a set of forces, so let's say there is a system and there is subject to some forces and it is under equilibrium. So it is saying that if I give some virtual displacement of the system, which obviously has to be compatible with the boundary condition, right? I mean, in the system boundary, like let's say cantilever wing, we cannot give virtual displacement in the fixed end, right? That is a fixed. Okay, so that is what we are saying, that this bracket term meaning this compatible with the system constraint. Okay, so then the total forces. What forces? The forces which is making keeping the system under equilibrium. Okay, so if I give some virtual displacement, so the work done by the forces which are the in going through this virtual displacement which are the zero. So we'll see. But for as we'll discuss the derivation of the equation of motion for a single degree of freedom system, maybe in the next class. So then you will see that this principle of virtual or the energy or this Lagrange equation of motion. You will figure what is this. This Newton law is very simple, or the D'Alembert principle very simple. But as I mentioned, for the complicated system, this will be much more useful. Okay. So yeah. So which method to use? So remember, all procedure leads to the identical equation of motion. So this is the convenience. Okay. And obviously, sometimes it is a personal preference also. Okay. But it generally depends on the nature of the dynamic system you are handling. Okay. Fine. So I'll stop it here. We'll meet tomorrow. And actually, just 1 minute. So there, no, so this terminology I'll discuss tomorrow. Okay, fine. Okay. I'll stop it here. So I hope I am able to give you some basic introductory idea, which is much simpler, and you refer some books also. Then it will be clear to you. Or someone has written Mario Parts. Okay, no problem. Okay, thank you.